Okay, guys, hopefully that's working now. We're going to go ahead and get started. Okay,
Quentin.
so you guys should have finished 6.6 on your own. We are going to go ahead and start on 6.7 notes. Okay, so 6.7 is about partial fractions decomposition. So I will talk to you about why we are doing this first of all. Okay?
What's a partial?
So when we see rational functions that look like this, okay, these are incredibly hard to work with, as you guys know, because you had to graph them, and they were kind of a pain, right?
Slant asymptote?
They have slant,
No.
this one's bigger on bottom, so it's why it's, y equals 0 would be its asymptote. But the top would be x minus 3 times x plus 2, but then the bottom is x squared times x squared plus 1, which is not pretty. Anyway, nothing gets easier, right? Like, we can't break this down into factors. And so what we do is what's called partial fraction decomposition. And the whole point of it is to try to break it down into something that is easier to work with, okay? So here's how it works. We figured out that if you have some polynomial on the top, p of x, and if you have some polynomial on the bottom, q of x, p over q, you guys have heard that before? Yes, we're trying to be consistent here. Okay, then you can break it up into these fractions that have a very specific pattern to them, and it comes out equivalent. Okay, so the point is to make it easier. I know that looks scary, but I promise it makes it easier in the long run. So rather than trying to explain to you what this all says before you know what the heck I'm talking about, we're going to do an example. After I've done the example, I will go back and explain where certain things are, if necessary. Does that sound okay to everyone? Yeah? Okay, so if we have this thing, this gross rational function, and we try to factor it, you can factor the bottom. You cannot factor the top. So we'll start there. We'll factor the bottom because we can. What does the bottom factor into, guys? Good. 6 times 4 is 24. 6 plus 4 is 10. That's exactly what we wanted. Okay? And I'm actually going to switch those. I like to have the smaller one first. Why? Does it matter? No. It just bugs me. There's literally no reason for it. Okay. So that's great, the bottom factored, but the top is still 5x plus 16. There's really nothing you can do with that. It doesn't factor evenly, there's no GCF, it's just kind of ugly. So here's what we do. To be able to deal with this, we split it into multiple fractions. So what we're saying is that some value, a, over x plus 4 plus some value b over x plus 6 is going to equal this. Okay, so if we're looking at this right side right now, those are two fractions that we cannot add. Why? Why can't we add those two fractions?
They have different denominators.
They have different denominators, right? Okay, but what if we made them have a common denominator? Then could we add them?
Yeah.
Sure. Well, how would we get a common denominator for these two things?
Cross multiply.
Yes and no.
Oh,
Yes and no. That is the shortcut, and we will get there, but I want to do it the long way first.
so
Okay.
multiplying both sides by x.
So we need to multiply both sides, or top and bottom, by the other one to get a common denominator here. So why do I have to multiply it by top and bottom? You have two choices when you're multiplying things. You can either do the same thing to both sides, or you can multiply by 1. Those are the two things to not change it, right? Multiplying by x plus 6 over x plus 6 is just multiplying by 1, right? My professor always called it a convenient form of 1, okay? Why are we doing x plus 6 over x plus 6? Because of this, but we need it to be equivalent to 1. Does that make sense? Okay, and then the other one is the same thing, except for this time we're going to do x plus 4 over x plus 4. It's the opposite one, right? So then if we actually multiply these things in, here's what happens. We get a times x plus 6a over x plus 4 times x plus 6. You guys okay with that? Yeah? And then the other one, if we actually multiply this one in, we get b times x plus 4 times b divided by, what happens with our denominator? We end up with both of them, right? And what we're saying is that these things are equal. Are you guys okay with that? Now, we still don't know what A is, we still don't know what B is, but we know that there is some value that exists for A and B that this is going to be true for. Okay? So, now that we have all of the same denominator, we actually don't need it anymore. Okay? Which is what cross multiplication does, is it gets rid of the denominators. Okay? We really don't need it anymore. Why? Because if you were to say 5 halves equals 3 halves plus 2 halves, that's true, right? But also, isn't 5 equal to 3 plus 2 on the top? You don't need your denominators anymore. When they're all the same, the tops all become equivalent also. So we can ditch it now. We can ditch our denominator and just say 5x plus 16 is equal to ax plus 6a plus bx plus 4b. Are we okay with that? Okay. So now what we need to do is we need to find our like terms and compare them. So I'm going to take anything with an x. I'm going to find anything with an x first. And I'm just going to kind of highlight it for a second. That has an x, that has an x, and that has an x. Yeah? You guys okay with this? So what we're saying is that whatever the value of A is and whatever the value of B is, together they have to make 5. Right? Like if this were 2x and this were 3x, that would work, wouldn't it? Or if it were 4 and 1 or 1 and 4. There's different values that this could be true for, right? But whatever they are, A plus B has to equal 5. We okay with that? You can also think about it like ax plus bx equals 5x, but then I can just divide everything by x, and what happens? We're just going to get a plus b equals 5. That's why I don't really worry about it, but if it helps you clarify what's going on, that's what's going on. Okay, and then we're going to take everything that doesn't have an x, so 16, 6a, and 4b all do not have a variable, right? So we're going to say 16 is equal to 6a plus 4b. I'm going to flip that around, actually.
This is where the matrix comes.
This is why we're doing this with the matrix unit. Sajid figured it out. This is a system of equations with two variables, a and b, right? So now all we have to do is solve it. And we're going to do it with a matrix because that's what we're working on right now. Yeah? Which method do you guys want to use?
Kramer's law.
You can do whatever you want. I don't care what
Because
you
it's
do.
a 2
There's
by 2.
multiple rules.
There are multiple
Kramer's
rules. You can
rule.
use whichever one you want. So let's go ahead and
I
put
like
it in a
Kramer's.
matrix first of all. So 1, 6,
Inverses
1,
and
4.
no operation. Yeah. I'd rather do
Kramer's
Kramer's
rule.
rule.
Thank you.
Yeah.
From, what was his name? Like Albert Winston? Something like that.
I don't think I ever told you.
We've searched it though.
Okay.
Isn't it Gabriel?
It's,
Gabriel,
yeah,
that's what it
Gabriel.
was.
Oh yeah, he had a super white name. I remember.
Oh my gosh. This is being recorded. Can you please not say that? Okay. So this is our matrix or our system of equations, right? And if you want to use Kramer's rule to solve it, that's fine. We can do that. So the determinant, first of all, of 1, 1, 6, 4 would be 4 minus 6, which would be negative 2. Yeah? Do I need to slow down on that, or are you guys okay? Okay. And then the determinant with respect to x, we would ditch this column and put in our 5 and 16 and leave our y column, or b in this case, and do 5 times 4 minus 16 times 1. And 5 times 4 is 20, minus 16 is 4. We good with that?
Are we gonna get points for
I guess-
leaving it all out?
No.
Probably.
Okay, good.
I guess technically this shouldn't be x, though. It should be a, right?
Yeah.
Because this isn't really x and y. This is really a and b. All right. And then we do d with respect to b. So we leave the x's, switch out the y's. 16 times 1 minus 5 times 6, which is 16 minus 30, which is negative 14. Yeah? Double check my math.
Yeah.
Okay. And then, so that means that a is equal to whatever this is, which is 4 over negative 2, which is
Negative 2.
negative 2. And b is whatever this is, so negative 14 over negative 2, which is 7. Okay, but let's not forget the point of this, because this is not your answer. Okay? These are your values of a and b, but that's not what you were trying to do. You weren't trying to find a and b. You needed to find a and b to get what you were looking for, but what were you actually looking for?
An equation that would add to the
We need the two equations that would add up to this. So what we're saying is that 5x plus 16 over x squared plus 10x plus 24 is equal to a, or negative 2, divided by x plus 4, plus whatever b is, in this case 7 over x plus 6. This is our answer.
Everything in the scene that's so long.
Okay? Alright.
Do we have to use matrices to solve it, or can we just do elimination?
You can do whatever makes you happy. As long as you can solve it, go for it. You could have done elimination. It wouldn't have even been that hard. You also could have done substitution, which also wouldn't have been that hard. Go for it. Okay? Alright, so the point here is that we have these two fractions that supposedly add to make this, right? Now, I am not going to prove every single one of these today, but I will prove this one just to show you guys that it really does work, okay? So I'm just going to go ahead and prove that one to you. Just going to copy this really quick. I'm going to go through it fairly quickly, unless you guys have questions, okay? Okay, in order to add these, we need a common denominator, right? Or as Sajid said, we could also just cross multiply them. So negative 2 times x plus 6 plus 7 times x plus 4 should equal 5x, was it plus 16 or minus 16? Plus 16. Right? So we distribute in negative 2x minus 12 plus 7x plus 28 should be 5x plus 16. Negative 2 and 7 definitely make 5. Negative 12 and 28 make 16. Is this a true statement?
Yes.
I hope so.
Okay. So did it work? Did we get a true statement for our partial fractions? Yes. That's the easiest way to check your work on these. Try it. See if you can multiply them together to get the right answer. Yeah? Okay. Moving on. Actually, nope, I lied. All that this is saying is that if you have the rational function p of x over q of x, there are some values a, b, however many there are factors for q of x, okay? So a and b are all we used in this one because there were only 2 factors on the bottom, okay? If there were 3 factors, you would have this plus c over whatever that third factor was. Okay? And this happens specifically when we have distinct linear factors for q of x. Okay? So what does linear mean, first of all? What does a linear factor look like?
A line.
Some x plus some constant. Okay? X plus a constant. Or like 3x plus a constant would be fine too. Okay? The number in front does not have to be the same. Okay? But they have to be different from each other. Okay? So all this is saying is there's sum a over your first factor plus b over your second factor plus c over your third factor, etc. for as many factors as you have. We okay with that? Okay. So let's go ahead and look at the next part. So now what it's saying is that you have some polynomial on the top for p of x, but q of x is equal to some factor that has a multiplicity of n. Do you guys see the n? So it could be a 2, it could be a 7. It doesn't really matter. The way that it works is that you get a over a single one of those factors plus b over 2 of those plus c over 3 of them, etc., etc. Okay, so for this one, let's go ahead and factor first here. This is 7 times x plus 2, right? Over x plus 3 squared. Now, I'm going to tell you right now, the top factoring doesn't actually help you. But that is true. So here's how it's going to work. 7x plus 14 over x plus 3 squared will equal some value of a that we don't know what is, divided by x plus 3. Why is it x plus 3? Because that was your factor. Plus some b, also over x plus 3, but this time it's going to be squared. If it were to the third, you would just keep going. C over x plus 3 to the third, d over x plus 3 to the fourth. You just go as many times as you have technically n's, but whatever your degree or your multiplicity is. Okay? So this one's only 2, so we only need to go through b.
Gotcha.
Does that make sense how the pattern works, though?
So the
Okay.
multiplicity of the denominator is what determines how many values you will have.
Exactly.
Okay.
Okay? Really the degree of the denominator in general, because on the last one, the degree was 2,
2.
right?
Mm-hmm.
Which means we had 2. We had an a and a b. If it were 3, we would have an a, b, and a c. Okay, good. All right, so this one's actually even easier to get a common denominator, right? What would we have to do to get a common denominator on this one?
Multiply the a side, both by x plus 3.
And this is the only one we have to multiply anything by, right? The other one already has the common denominator.
Why does that work? Wouldn't you have to multiply both sides?
So it's because we're multiplying by 1. That's why I have to do it top and bottom. I'm multiplying by 1, which does not change this value, right? Anything divided by itself is 1. So I'm not really changing this value.
Okay.
Does that make sense?
Yes.
Okay. So 7x plus 14 over x plus 3 squared is going to equal, we're going to go ahead and times it in, ax plus 3a over x plus 3, we have 2 of them now, so I can say x plus 3 squared, plus b over x plus 3 squared. Okay, do I have a common denominator now? Yes? Then you can get rid of it. You no longer need it. Okay? We can say that 7x plus 14 is equal to ax plus 3a plus b. And then we're going to do the same thing. We're going to find every term that has an x. It's just those two, right? So what's the value of a?
7.
You didn't even have to do anything for that one. A is just 7. And then we can go ahead and find anything that doesn't have an x. And we can say that 3a plus b needs to equal 14. But I already know A, right? So I'm not even going to use a matrix on this one because it's unnecessary. You guys okay with that?
Yep.
Yeah? So again, that's what we needed to get, but it's not our answer. Our answer is that 7 over x plus 3 minus, why is it minus? Because b is negative. If you want to, you can do a plus, a minus 7. I'm just going to stick with minus 7 over x plus 3 squared. And we're saying that that is equivalent to our original expression, 7x plus 14 over x plus 3 squared. Okay? That's how that pattern works. Yes?
How come the first x plus 3 is squared?
Because that's how the pattern works. Do you guys remember doing like recursive formulas in 9th grade? Where you had to take like the previous term and do something to it,
I wish I could forget
Yeah.
it.
et cetera, et cetera. Well, I have bad news for you about chapter 7. That's why, Cleo. So the pattern that this, so like with recursive linear ones, it's like, okay, you always take the previous value and add 7, add 7, add 7, add 7, right? So for this one, the formula to get that pattern to hold looks like a single factor, 2 factors, 3 factors, et cetera, et cetera, et cetera. Kind of like how with a linear one, it would be whatever your previous term is, times by 7 if you're adding by 7, plus if you started at 2. So what you would do is you would start at 0, so 0 minus 1 is negative 1, 7 times negative 1 is negative 7, plus 2. So that would mean that your sequence would be negative 5, and then the next one you'd add 7, so then you'd be at 2, 9, et cetera, et cetera. And this is just the like general formula to be able to find those. Same thing here. This is just the general formula to make it look like this. This is just the formula to write it out. Does that make sense? Okay. I think that'll make more sense after we do 7-1. I hope. Okay. All right. So I want you guys to try this one out.
Oh, no.
I will help you with the factoring. So it's going to be 12 times negative 7. And they need to add to negative 17, right? And I will just tell you what they are. Because I'm nice like that.